Anyone can build a website if you use Squarespace, the sponsor of this video. For a long time, I had a big misunderstanding about Schrödinger's cat. What's Schrödinger's cat, you ask? Well, it's a thought experiment that Erwin Schrödinger, along with Einstein, came up with to express how unhappy they were with quantum mechanics. But what exactly is the thought experiment? Well, you trap a cat in a box with a radioactive atom, which if it decays, it triggers a poison, killing the cat. Don't worry, it's just a thought experiment. Now, if we close the lid so that nobody can see what's inside the box, the question is, what is the state of the cat right now? Now, here's what our classical thinking says, okay? Radioactivity is completely random, which means there's a 50% chance that atom is decayed or not. It's either one of them, right? And as a result, right now, there's a 50% chance that the cat is either dead or not. It's one of them, right? But that's not what quantum mechanics says. Here's what I thought was going on. I thought that according to quantum mechanics, as long as you don't open the box, as long as nobody sees what's inside the box, that atom is neither decayed nor not decayed. It's kind of both at the same time. And therefore, that cat is neither dead nor alive. It's kind of both at the same time. I thought this was the meaning of the word quantum superposition. Kind of like nature has not yet made a decision, but it's only when you open the box, one of them becomes reality. Now this sounds pretty mind-boggling, right? But I had so many questions about this. Like first of all, what does it mean to say that the cat is both dead and alive at the same time? And secondly, why does reality change based on whether you're looking at it or not? How does nature know? And thirdly, how do we know what's happening inside the box when no one's looking at inside of it? Like, how do we know? How can we even comment about it? We are not looking inside of it. I didn't get any satisfactory answer for a long time until I read Feynman lectures. Just by going through the first chapter of his volume 3, I realized that it's wrong to say that that cat is both dead and alive at the same time. That's not what quantum superposition is. It's much more profound. And so the goal of this video is not only to get a deeper understanding of what quantum superposition is, but also to rediscover all of these ideas step by step ourselves so that we don't have to take anybody's word for it. So if you're ready for this, let's begin. So Feynman, where do we start? Feynman says, if you want to rediscover things yourself, Mahesh, then the best place is to look at an experiment and try to construct scientific models all by yourself. There are a ton of experiments we can look at, but the one that Feynman loves the most is the electron double slit experiment. Now, the moment he says this, I'm like, Feynman, I'm going to stop you right there. I already know the electron double slit experiment. It's pretty famous in our times now. So I tell him that, hey, look, you take an electron gun and you shoot one electron at a time through the two slits. What we would expect is a pattern somewhat like this, right? Where you get two smears right behind the two slits. But that's not what we get. Instead, we get an interference pattern. And so we now wonder what's going on. This helps us understand that electrons don't just behave like particles. They kind of behave like probability waves, which passes through both the slits, and then the wave interferes with itself. And then when it finally reaches the screen, the kind of wave collapses, and that's where you get the particle. That's where you get the electron. And that's basically what's going on over here, right? Feynman, right? And Feynman says, Mahesh, the only thing that's interfering over here is your superficial half knowledge. It's fooling you into thinking that you understand quantum mechanics. Please, please, for the love of God, keep all your preconceived notions aside, at least for the next few minutes, and think about what I have to say with a fresh mind. Because I'm going to show you a perspective that you probably never thought of before. And I'm like, all right, fine, I'll play along. And I did get to see a perspective on the double slit experiment that I had never thought of before. So again, we're going to take our electron gun, shoot one at a time through the double slit, and wait for the pattern to generate. And eventually, the pattern that we get looks like an interference pattern that we get when you send waves through it. So now Feynman asks, Mahesh, the question over here is, which slit did the electrons go through? Now, I'm like, in the back of my head, I already know the answer to this. A single electron actually goes through both the slits and then sort of interferes with itself. That's the only way to get that pattern. But Feynman has asked me to keep my preconceived notions aside, so I'm not going to talk about that. So I'm like, okay, Feynman, how do we answer this question? Feynman says, well, let's go through some options. Maybe the first option is all the electrons went through slit 1. Now, I know that that's wrong, right? But Feynman says, okay, but how do you test it? How do you test whether this option is right or wrong? Here's how you do it, he says. You close slit 2 and redo the experiment and think about what pattern we would get. Now, if the pattern we got is the same as the pattern we originally got with the double slit, then that option might be right. If we don't get the same pattern, then that option would be wrong. So Feynman asks, Mahesh, if I close one of those slits, what pattern would you expect? Well, if I close one of those slits, the pattern we get would look somewhat like this. We get a lot of electrons right behind the slit one only. And clearly that's not the pattern that we got in the double slit. So from this we can say that, hey, all the electrons did not go through slit one. So this is how we're going to answer all our questions experimentally. Okay. All right. So the next option is maybe all electrons went through slit two. Now, how do we check that? Well, the same way. Now you close slit one and see what pattern we would have gotten. And the pattern that we would have gotten would look like this. We would get a patch right behind the slit two if this was the case. But again, our pattern is not that. We get an interference pattern. So clearly they're not the same, which means the electrons did not go through slit two. All the electrons did not go through slit two. Okay, what other options are there? Well, maybe we would say some electrons went through slit one and others went through slit two. Again, how do we experimentally check for this? Well, if this was the case, we would have gotten a combination of the previous two, because we know what pattern we get when electrons go to slit one. We know what pattern we get when the electrons go to slit two. So if some go to slit one, some go to slit two, there we should get a combination that will look like this. But again, that's not what we got. We got an interference pattern. So from that, we can say that that's not what happened. And so now Feynman's like, Mahesh, what else is there? Well, I'm like, all right, Feynman, what if each electron is somehow going through both the slit? Isn't that the answer? And Feynman is like, well, let's test it. If a single electron is going through both the slit, then if I were to bring the screen all the way close to both the slits, then every single electron should give me 2 dots, right? Right? And I'm like, no. I don't mean the individual actual electron. The probability wave is what is going through. And Feynman is like, Mahesh, what did I tell you? Do not use your preconceived notion. Let's think about this rigorously. You said that each electron is going through both the slit. What is the meaning of that? If each electron is going through both the slit, then I should get 2 dots right behind the slits, right? And I'm like, yeah, right. But does that happen? It doesn't. You will always find, if you keep the screen right next up to the slit, you will always find only 1 dot, which means this option is also wrong. Each electron does not go through both the slits. Okay. What if the electrons are going through neither of the slits? That's possible, right? And Feynman is like, Mahesh, now we are thinking rigorously. But again, how do we test it? Well, if electrons are going to neither of the slits, let's redo the experiment. This time we'll close both the slits and see what we'll get. This is what it means for electrons to go through neither of the slits, right? But if you close both the holes, then you would get nothing on the screen. So clearly that's not what we got. We did get something on the screens. That means even this option is wrong. What else? And I'm like, oh my God, I'm running out of options over here. But wait, we're not going to give up. Maybe electrons are doing something way more complicated. What if an electron is, say, going through slit 1 and then coming back to slit 2 and then again going like this? And Feynman says, again, you can test for it. If an electron is going through slit 1 and then coming back to slit 2, then if I keep a barrier over here, I should be able to detect it. But that never happens. If I keep a barrier, I will never ever detect an electron being detected over here, which means that's also wrong. Any complicated path that you can think of, that's also wrong. And I'm like, we've exhausted all the logical options that we can think of. I mean, there is no other possibility, right? And yet, electrons are somehow going through both the slits in a way that's not any of this, but it's inconceivable. It's almost as inconceivable as, I don't know, having, say, a single tool that can help anyone build a website like Squarespace, the sponsor of this video. Squarespace says it's an all-in-one website building tool. I'm like, really? Well, to build a website, the first thing I need is to get a domain. Can Squarespace help me with that? Yes, just click on Get Domain, pick an available domain name, and boom, within a few seconds, your domain will go live. And it comes with Whois Privacy for free, which, is necessary if you feel like your privacy needs to be protected. Okay, I have my domain, but I don't even know where to begin to build my website. Squarespace says, no worries. Just pick a particular type that you would want, like say a portfolio, and then pick a template that I would like. But wait. I don't want my website to be templatized. I want it to be unique. I have a dream. I have a vision. And Squarespace says you can hyper customize it, buddy. You can change pictures, change font, change all the layout, do whatever you want just by clicking buttons. And guess what? In a few hours, my website, FloatHeadPhysics, went live. Yep, I'm pretty happy with how it turned out. Okay, now that it's live, I want to check how FloatHeadPhysics.com is doing. Squarespace says, look, there's this analytics section over here. Click on that and you will get different kinds of data. And before I ask, it also has a dedicated support to unblock me if at all I get stuck anywhere. So yeah, I think it's pretty cool. It has it all. So if you want to build any kind of website, you can try Squarespace for free. Just go to squarespace.com/FloatHeadPhysics. And if you decide to make a purchase, you can even save 10% by using the promo code FloatHeadPhysics at the checkout. And so if you want to share stuff with the world using a website, then do check them out. The link is also in the description. Now back to the video. So Feynman, what is the answer to this question? Which slit did the electrons really go through? I mean, we've looked at all the possible options that we can logically think of and all of them are wrong. So what do we do? And Feynman says, well, Mahesh, apparently this means electrons are going through both these slits in a way that we can't even logically conceptualize. It means that we can't use our words or vocabulary or pictures to communicate what they're doing. What they're doing is a completely new behavior, and that's why we come up with a new name for it. We call it the quantum superposition. We say that the electrons are in a quantum superposition of going through slit 1 and going through slit 2. But I'm like, what does that mean? Okay, and Feynman says, I cannot tell you what that means using any words that we use to communicate or any pictures. If I try to do that, I will only cause miscommunications. So the best I can do, Mahesh, is I can tell you what quantum superposition is not. It's none of the above. It's its own new thing that cannot be explained using any prior knowledge that we have. At first, this is deeply frustrating, right? But if you think a little bit more about it, it actually is quite satisfying because Feynman is actually showing us why it is impossible to use our language, our words, or pictures to explain what quantum superposition is. If you try to do that, you're going to cause misconceptions. And that's why it's even wrong to say quantum superposition is kind of like the electrons are going through both the slits. No, wrong. Don't use any words. You can only explain what quantum superposition is not. You cannot use words or pictures or animations to describe what it is. It is a brand new thing. It's its own thing, and you cannot use any prior knowledge to explain what it is. And that is truly profound. That is beautiful. But what's even more beautiful is that you can use math to describe exactly what quantum superposition is, and you can communicate it mathematically. And that's why math is the language of quantum mechanics. So Feynman, are you saying that it's wrong to think of electrons as a probability wave that passes through both the slits and then interferes with each other and they collapse, right? Well, Feynman says it's not wrong to say that, but you need to understand that is an interpretation of what the underlying math is telling us. This is called the Copenhagen interpretation, is the most famous one. There are other interpretations, first of all, but more importantly, science never tells us which interpretation is right, okay? And that's important. This is just the way we interpret the results, the math over here. That's important, okay? It's not what the experiments are telling us that that's a fact. But more importantly, when we say, for example, probability wave, what do we really mean? I mean, when you think about a wave, what comes to your mind is that something is going up and down and then energy is being transferred. But over here, none of that is happening. So it's not a wave in any traditional sense. It's just called as a wave because the mathematical equation that describes it is very similar to the wave equation. And so there are all these caveats and disclaimers that come when we're using those words, and we need to be very careful about it. And that's what Feynman is saying. When you're trying to use those words, you need to be very careful. Otherwise, we might just fool ourselves. Okay, so the final question we could be having then is, why doesn't quantum superposition happen at a macroscopic level? If it did, then we would all have intuition for it, right? Why does it only happen at the microscopic level? Feynman says that's a great question. For that, we can go back to our experiment. See, over here, people were really annoyed with the fact that none of these is like, electrons are not doing any of these things, right? They're doing something completely different. So they really wanted to find out if they could somehow detect what the electrons are really doing. And so for that, they decided to use a detector. See, so far they were actually doing this experiment in complete darkness so that nothing was interacting with the electron, not even light. But now they thought, what if they use a tiny light source? They keep it between the two slits, such that when electron passes close through a slit, the light can be scattered off and then if it reaches our eyes, we can see a flash. And by looking at that flash, we may be able to identify where the electrons are really going. So for example, if we conduct this experiment with that light source and we see a flash going in front of this, let's say slit 1, then I know electrons went to slit 1. If it goes in slit 2, then I know electrons are going to slit 2. So this way I can really detect what's going on. So people redid this experiment with that light source, and guess what they got? This time, they actually found flashes in front of slit 1 and slit 2, which means that the electrons were indeed, some of them were going to slit 1 and some of them were going to slit 2. So that was indeed what's happening. But when we look at the pattern now, we no longer get an interference pattern. We get the pattern that we would expect from particles. We get 2 patches behind the slits. So what does it all mean? And I'm like, I know Feynman what this means. This means when there is no observer, we do this in complete darkness, we get an interference pattern. But when we have an observer, that interference pattern is gone. That means the act of observing changes reality. That means consciousness affects reality, right? And Feynman says again, Mahesh, no, all of that is hocus pocus. No, none of that happens. What's really happening, again, if you were to be rigorous and be scientific, what's really happening from this experiment, what we can conclude is that when there was no light source, the electrons were behaving, they were in a quantum superposition. But because of the light source, the electrons started interacting with the light. When they interact with the light, now they are going through one of the slits. That means they're no longer in quantum superposition. So that means when you interact with these particles, with light or with anything else, the quantum superposition is lost. So this is not just true for electrons going through the slits, it's true for any quantum properties. For example, consider the spin. When you measure electron spin, you might get it to be spin up or spin down. But if there are no measurements being done, if there are no interactions, then the experiment shows that the electron doesn't have an upspin, nor a downspin, nor both, nor neither. They would be in a quantum superposition of being up and down. And again, that does not mean they're up and down at the same time, and I cannot show any visuals or any animations to explain what quantum superposition is. But when you measure it, you'll always find it to be spin up or spin down with a 50% chance. And this is what Erwin Schrödinger and Einstein didn't like, because this meant that nature is no longer deterministic. I cannot, with 100% certainty, predict the outcome of what the measurement will give me. Quantum mechanics was saying that nature is inherently probabilistic, and they didn't like that. And to express that dissatisfaction, they came up with the thought experiment. And now the thought experiment makes sense. When you close the box, you're basically saying, assume there are no interactions happening inside. Then what is the state of the atom? That atom is not decayed. It's also not decayed. It's in a quantum superposition of being decayed and not decayed. That does not mean it's both decayed and not decayed at the same time. Hope you understand that now, right? And therefore, what is the state of that cat? It's not dead, it's not alive, it's also not both, it's also not neither. Its state is a quantum superposition of being dead and alive. And it's only when you open the box, the state changes. The quantum superposition is gone, the state changes to being either dead or alive. And so their argument was, does it make sense for that cat to be in quantum superposition? No, right? And therefore, quantum superposition is not real. But today we know it is real. With all the experiments, the double slit experiments, the experiment with the spin, we have a lot of experiments that show that the quantum superposition is indeed real. But of course, it doesn't apply to macroscopic objects like cats, because there are a lot of interactions happening. Remember, it has nothing to do with conscious observers looking at it. It has something to do with interactions. Macroscopic objects have a lot of interactions, so it doesn't apply to macroscopic objects. But quantum superposition is real. As long as you don't measure something, as long as something is not interacting, their state is in a quantum superposition. So the final question we could be having for Feynman is, since quantum superposition only acts at the microscopic level, and that too when there are no interactions happening, and we live in a macroscopic world with so many interactions around, does that concept really have any significance? And Feynman says, think about this. Consider an electron that is going around a nucleus. Now imagine another nucleus comes close by. Then that electron has a choice of orbiting the nucleus 1, or it could be orbiting nucleus 2, or it has a choice to orbit both the nuclei, or it has a choice to not orbit any of the nuclei. What will that electron do? None of the above. It will now be in a quantum superposition of orbiting the nucleus 1 and the nucleus 2. And by the way, when we say the word orbit, that's wrong. Electrons are not going around the nucleus. Even here, we can think that electron is in a quantum superposition of different places that it can all be. This is what we call an orbital, but again, that's a side note. Anyways, over here with the two nuclei, what you can see is that this quantum superposition is what is keeping the two nuclei together, is creating a chemical bond, which we call the covalent bond. A covalent bond is a quantum superposition. It's not really that electrons are being shared between the two nuclei. That's a word that we use to make things easier to communicate, but that's wrong. It's in a quantum superposition. Without it, we wouldn't have covalent bonds, which means we wouldn't have water molecules. We wouldn't have molecules in your DNA, proteins. Life itself wouldn't exist without quantum superposition. So if you think about it, Schrödinger originally came up with the thought experiment, along with Einstein actually, to tell us why they were unhappy with quantum mechanics. But it turns out that the thought experiment is actually useful in explaining why you and I and this world exists in the first place. If you like this video, you'll also probably like my previous video on how a simple accident, a lab accident, unlocked the whole quantum revolution. Do check that out over here. See you.